This is the third lecture in Unit 4. It's about calorimetry, and you already learned the basics of the calculations that go with calorimetry when we did Q equals MC delta T calculations in the last lecture, but we're going to use them a little bit differently today, so there are some tricks that come with just calorimetry. So this is how it's a practical application of what you already know from the last section. So the first thing you're going to want to do, if you haven't already, would be to stop the video and do the learning targets. These are pretty short and quick, so make some good comparisons between coffee cup calorimeters and bomb calorimeters, and the formulas you use and the similarities and differences, but then make sure that you leave lots of space for notes and examples, and we'll come look at them again together. So pause the video if you still need to, and come back when you're finished. Okay, so the first thing that I want to stress for you about calorimetry, regardless of the type of calorimeter that you're using, is that we have two things that we need to consider. And the first would be that the amount of heat flow that we measure in calorimetry is specific to the amount of stuff that's in the calorimeter. So if we want to translate this to a heat of reaction where it matches the coefficients in a chemical equation, we often have to convert it to the amount of joules or kilojoules per mole of that same stuff. And then we have to make sure that it actually matches the coefficients in the equation. So if your coefficient in your equation is for 2 moles, then you have to consider how much heat it would be for 2 moles, not just for 1. So this gets to be a little bit tricky, and I think honestly this is the trickiest part of all of thermochemistry, is remembering that you need to know exactly how much stuff your heat matches at all times, so that you can always make sure that it is equivalent to the amount of stuff that they're referring to when you're being asked questions. Often in calorimetry, we deal with the heat of the amount of stuff in grams, not in moles, and so that's another difficulty. The other thing that's really important for both types of calorimetry is that always in calorimetry, we are referring to the surroundings. This works for coffee cup calorimeters as well as for bomb calorimeters. And the calorimeter itself, the water in the calorimeter, the thermometer, or just the calorimeter itself, if it's a bomb calorimeter, are definitely the surroundings. And so we have to every single time make that relationship between Q of the calorimeter is equal to the opposite exactly equal amount. We're going to assume there's no heat lost or gained by anything. Exactly the equal and opposite Q of the process that's happening in the calorimeter or of the system. Okay, so this is really, really important. Those things are super important as you're going. We also always make the assumption that there's no heat lost or gained, and this is a really big source of error. So let's talk about coffee cups first. I think that they're trickier, so we might as well get the harder part out of the way. Like I just said, Q of your system is equal to the negative exact same size but different sign of the Q of the surroundings. And we will calculate Q of the surroundings from the data that we collect. So you'll always have to remember to change the sign and call it Q of your reaction or of your process of whatever's happening in there. So this is really kind of a tricky situation, and you always will have to struggle to think about that. It's not a calculation, it's just to change the sign and make sure you know how much it matches, how much stuff it matches. So some tricks that are really important when you do this. If there's some interaction between the water in a coffee cup calorimeter and the stuff that you're putting in it. So if it's a dissolving process or a reaction of two solutions, you have to make sure that you include the mass of both substances in the mass of the surroundings in your calculations. All right. So if we're dissolving 5 grams of something in 100 grams of water and measuring the heat that either goes in or comes out, the total mass would be the 5 grams of the salt plus the 100 grams of the water. So 105 grams would be used as the mass of our surroundings. This is because as soon as it's dissolved, the mass that has to have the temperature change occur to it is the mass of both together. This is definitely a stumbling block. You will definitely encounter this, and it will be something that you will be required to think about. So just always think about that. The specific heat capacity in these cases is almost always the same as, sorry, that's the lunch bell, is almost always the same as that of liquid water because the solutions are really dilute. So this is something that you don't have to question. If it's hydrochloric acid solution and they don't give you a new specific heat capacity, you're using the specific heat capacity of water. The solution that you're making, you're using the specific heat capacity of water. So this is almost always the case, and they will make a really big deal of telling you if the specific heat capacity has changed because of what you've done. Remember also that the thermometer is reflecting the change in the temperature of the surroundings, and that if you have something hot that you drop into your calorimeter, that the final temperature, or the mixture of the two things that you put together, the final temperature of both will be the same, that they will exchange heat until their temperatures are identical. So they might have different initial temperatures, but they will definitely have the same final temperature. And of course, that idea, if you're doing error analysis, that no matter how much we try to isolate the system, the cups, the lid, and even the air around it will still absorb heat. If you're holding on to the cups, you're going to feel heat, or would still give off heat. If it's going to feel cold, you're going to feel that. So we ignore that, but that is definitely a source in the lab of error. So think about that if you're being asked about error analysis with calorimetry. So let's do an example quick so that we can see what's happening here. We have a fairly straightforward example here with no reaction or change in our calorimeter, and then I'll do another one where there is a reaction, is a change in the calorimeter, so that we can see how that works. And so this first one, we're just going to take a metal and we're going to heat it up and drop it into cold water and see how much the temperature of the water changes, so that we can identify who the metal is. And so we're going to identify it from the specific heat capacity. Sorry, I cut this off. This is the specific heat capacity in joules per grams degree Celsius of each of these metals. All right, so the thing that I want to remember is that Q of the metal will equal the opposite sign, an equal amount, as Q of the water that we drop it into. And I can solve for Q of water by knowing the mass of the water, the specific heat capacity of the water, and the temperature change of the water. All right, so all three of those values have to be about the water, and then I can translate it backwards to the metal. So let's do this really quickly, where Q of the water equals the mass of the water, which was 25 grams, times the specific heat capacity. This is liquid water, so that's 4.184 joules per grams degree Celsius. You should probably know that value. And the temperature change from 25.55 to 27.25, so final minus initial, 27.25 minus 25.55 degrees Celsius. And when I subtract that out, I get a difference of 1.7 degrees, so that's going to technically be 2 sig figs. So I'm going to solve for Q and discover that this is positive 177.82 joules. I'm not going to round it here because I'm going to wait till the very end to round, but know that this technically has only 2 significant figures. Okay, so now I can say this is the Q of the water. If I want this to be the Q of the metal, I have to change the sign. So Q of the metal will equal negative 177.82 joules, which then equals the mass of the metal times the specific heat capacity of the metal times the temperature change of the metal. So we're going to plug in these values and solve for specific heat capacity. So this would be negative 177.82 joules equals the 12.18 grams of the metal times its specific heat capacity that we're solving for times the temperature change of the metal. And here's where our important knowledge comes in, and that would be that we started at 65 degrees, the metal was hot, we dropped it into the cold water, and its final temperature was the same as that of the system. So the whole thing, the system and the surroundings, have the same final temperature of 27.25 degrees, but the metal started at 65. Okay, so this is a difference of 37.75 degrees Celsius. So I'm going to go ahead and do the algebra to solve for specific heat capacity and see that this comes out to positive. Specific heat capacity will always be positive. 0.39, because this is a negative temperature change. Let me step back. The negative temperature change and the negative heat give me a positive specific heat capacity. 0.39 after I round this to two significant figures, joules per grams degree Celsius, which allows me to come up here and identify the substance as copper. Okay, so this is how we do this when there's no change, no reaction occurring. I am going to do an example where you have a reaction occurring. So in this case, we have a reaction between sodium hydroxide and hydrochloric acid. And I'm going to have to write that equation because eventually they want delta H of the reaction, which means that I need to have this match my coefficients. So I'm going to go ahead and balance the equation. That would give me sodium chloride and water. This is an acid-base reaction, and it's balanced the way it is. So all of the coefficients in there are ones, and this makes this pretty straightforward. Okay. The next thing that I need to figure out is whether or not there's a limiting reactant. So notice that they gave me 100 milliliters of each of my solutions, and they're both 1 molar. So this means that because I have the same volume and the same molarity, I have the same number of moles. Right now, I don't need to know the number of moles, but I'm going to find it because later, to find the heat of reaction, I need my heat to match 1 mole of either sodium hydroxide or hydrochloric acid. So I'm going to go ahead and do 100 milliliters, 2 liters. So that's going to be, oops, sorry, backwards. So that's going to be 1,000 milliliters in 1 liter. And and then the molarity was 0.1 molar. So this is 0.1 moles per liter, which gives me a total here of 100 milliliters. I think I did my math wrong. Let me just double check this. 100 divided by 1,000 times 0.1 is 0.01 moles. All right, so 0.01 moles of each. All right, 100 milliliters of, this is where my problem is. Sorry, this didn't match my work and I couldn't figure out why. I'm going to back up. This is 1 molar. Okay, so this is of 1 molar. So this is 0.1 moles of HCl and NaOH. Okay, so this is important because my coefficients are 1 mole, which means when I'm done, I'm going to have to translate this to per mole instead of per 0.1 moles. Okay, so I'm going to do the same process. I'm going to do Q of the reaction equals the negative Q of the surroundings, which is really in this case water. Okay, and or my solutions, and I'm going to see that they have the same density as water, which is 1 gram per milliliter. So I have to start with 100 grams, 100 milliliters, or 100 grams of HCl and 100 grams of NaOH, and that means that my total solution that's changing, that's changing temperature will be 200 grams of solution. Okay, so we are going to come in here and I'm going to change this so it's a little less confusing to Q of the solution. So Q of the solution will equal the mass of the solution times the specific heat capacity of the solution times the temperature change of the solution. And I'm going to plug in what I know. And that would be 200 grams of solution. It tells me that we're using the same specific heat capacity as water. And the temperature change of the solution, they started at 24.6 and ended at 31.3 degrees Celsius. So this is a temperature difference of 6.7 degrees Celsius. So Q of the solution is positive, the temperature of the solution went up, positive 5606.56 joules, which then Q of the reaction would be negative of that value, 5606.56 joules. Okay, this does not have this many significant figures. Notice that I really only have 2 sig figs, so I want to kind of keep that in mind. That's for my temperature change. Equals this many joules per 0.1 really 0.10 moles, because this was 1.0 molar, 0.10 moles of HCl or 0.10 moles of NaOH. So we can choose either one, it doesn't matter, they are the same and their coefficients are the same. So I need to translate this. I'm going to actually add a page so I have a little bit more space. Sorry. So I'm going to translate this. So it's negative 5606.56 joules per 0.1 moles, and I need it to be per 1 mole. So if I divide this out, then it will be per mole of joules. And so, and actually joules are pretty cumbersome here, so I'm going to make this kilojoules. So I'm going to move this 3 to the left, and go from there, and then divide by 0.1. And so when I do that, I get negative 5606, and I can only keep 2 sig figs, so that will be negative, this is a mess, sorry guys, let me back this up. Let me confuse you even less, okay? So I want to convert this from joules to kilojoules. Let's do that. Show my work. So this will be negative 5.60656 kilojoules per 0.10 moles. And when I divide that out, I get negative 56, 2 sig figs, kilojoules per mole. And now, because it matches the coefficients in the equation of 1 mole, this is per 1 mole, I can say that this is delta H for that reaction. Wow. So if I wanted to write this as a thermochemical equation, I could write it as NaOH plus HCl yields NaCl plus H2O, and delta H is negative 56 kilojoules. Okay, so this is a really important thing. We have to make sure that the amounts match. All right, finally, the last question and the last thing I want to talk about is bomb calorimetry. This is way simpler because you don't have water in there and a specific heat capacity to worry about. Somebody's going to tell you the capacity of the calorimeter. They're fancy. This is a really fancy picture of one. We can pump in oxygen so that we can do combustion reactions. They're usually filled with water surrounding that chamber. But instead of worrying about how much water and the mass of all of that, the only thing we worry about is the capacity of the calorimeter. Okay, so what I want to do is this question that uses this information with you really quickly. So we have a manufacturer claiming that the new dessert has fewer than 10 calories per serving. To test this claim, we're going to place 1 serving in the calorimeter, and the temperature change goes from 21.862 to 26.799. So I'm going to set this up. Q of the calorimeter equals, let me get this out of my way, equals the capacity of the calorimeter times the temperature change. And they gave me the capacity as 8.151 kilojoules per Kelvin. Don't let that Kelvin scare you. The temperature change, the final was 26.799 degrees Celsius minus 21.862 degrees Celsius. So that temperature change is a difference of 4.937 degrees Celsius. Remember that the change in Kelvin is the same as the change in Celsius. So Q for the calorimeter, when I multiply that out, is 40.241487, okay, kilojoules. And they want to know per serving what this is in food calories. These are capital C calories, which are food calories. So kilocalories and kilojoules are the same thing. So I'm going to do this because food calories are really kcals. All right, so I'm going to go to this. 1 kilocalorie is the same as 4.18 kilojoules. And I discover that the calorimeter absorbed 9.617 kilocalories, which are food calories, from the serving of food that we put in there. This is still the calorimeter. If we were talking about the food, this means that it's negative 9.617 kilocalories that the food gave off. And so we could say that, yes, there are fewer than 10 calories per serving. So this is kind of how you use the two. We'll practice in class.